The Netherlands, a small country of only 41.5 square kilometers, is located along the western part of Europe. Specifically, near to the coast, the small city of Delft is situated. It is a historic location, home to 100,000 inhabitants, 20,000 of which attend the infamous Delft University of Technology. Delft is not only notable for its world-leading university, but it is also known for its canals, its bikes, and its wind. It is evident it becomes difficult for one to ride their bike on windy days such as this. The architectural context of this area plays a large role in causing the unsafe situation, and it was this problem that was chosen to be investigated within our group. The TU Delft campus contains the second highest tower in all of Delft, which houses the Faculty of Electrical Engineering, Mathematics, and Computer Science. It is 90 meters in height and contains 22 floors of office and classroom space. The wind, when it reaches the site of the iwi, is redirected around the building. It builds in velocity as it travels around the building's edges and therefore reaches the sidewalk with an increased force. If the wind were to be able to travel in a direct path, no longer obstructed by the iwi, there would be less of an urban problem. Therefore, the decided goal of our project was to investigate if we could decrease the high wind speeds around the iwi. The building itself is oriented with its longest facade of 85 meters facing in the southwestern direction, which is also the direction of the prevailing winds. The iwi acts as a large obstacle in the path of the incoming wind, and as a result, forces the wind around its form. This creates very high wind speeds on the leeward side of the building. The force of this wind is what causes people to be blown off their bikes. In order to understand what is happening around the iwi building, one can think of the funnel effect. Particles travel through the large opening of the funnel and are then directed towards the more narrow opening at the opposite end. Due to the fact that there is now a great abundance of particles flowing through a smaller area, the result is an increase of the particle speed. The same volume of particles enters and exits the funnel, but their velocity has changed. This is precisely what is occurring around the iwi building. Instead of traveling in a direct route, the wind is being redirected around the building to a smaller and more limited area that then allows it to continue along its path. The wind is being forced to travel by means of a constricted course, and therefore, when the wind rounds the building's corners, it moves at an increased and dangerous speed. In order to avoid such a situation, we must allow the wind to continue on its direct route. By opening up spaces within the obstructing building, the wind can proceed along its original path. This will decrease the pressure on the leeward side of the iwi and create lower wind speeds. The result of this intervention will create a much safer environment for the pedestrians and bikers that are passing by. When applying this hypothesis to the real-world situation, the question of where and how the building should be opened up comes into play. What size do we need for the gap? This inquiry was investigated by means of two different approaches. The first investigates opening up entire floors of the existing building. This will transform the usage of the floor from one that is inhabited by people to one that is only used by the wind. This design will allow for large amounts of the wind to travel through a limited number of places. The second approach explores enabling the wind to flow through elevated floor slabs. This will maintain the current building design. This organization will allow for smaller amounts of wind to travel through the building in a greater number of places. What additionally must be investigated is how the wind will travel through the iwi. Each design must analyze the point of entry of the wind within the building. Should the entrance be square, rounded, or angled in order to allow for the most accessible and efficient wind entry? Each design must analyze how the wind will travel through the building. Should the passageway be large, small, or change in size in order to allow a fluid passage of air from one end to the other? Each design must also analyze how the wind will exit the building. Should the exiting nozzle be directional, dispersing, or does it at all affect the characteristics of the wind as it is released into the urban situation? If you want to find out what options we used in order to save the biking student, then come to TU Delft and see for yourself. Thanks for watching.